I'm Itamar. I work at Astria. We're working on like a sequencing layer rollup infrastructure project. This is joint work with Stefanos, with also Adria, Akis, and Ben Lifshitz. I guess before I get into background, kind of like high-level overview is we're trying to analyze like the cost of operating ZK rollups kind of on an end-to-end basis. And so the background for this is everyone's favorite triangle. The blockchains are very slow. We've been trying to scale them. The problem has been summarized in this triangle before. We've kind of moved a couple eras since, but generally, like you got to choose. You used to have to choose between like 2 of 3 of like scalable, decentralized, and secure. Kind of fundamentally because like to validate a block, all the nodes in the system had to like re-execute the block. And if you have like 1,500 validators or however many you want to have, like getting everyone to do that in like a couple of seconds, very expensive. So you end up having to deal with these trade-offs of like, do I have a very small amount of validators that re-execute it to validate the votes? Do I have a large amount but then it's slow, or and that kind of thing. And then since 2020, kind of the new consensus on this has been like using rollups to scale this, where like this diagram kind of summarizes what a rollup is to those who are not as familiar. The main idea is like take a bunch of blocks, you roll them up into a block, you do all of this work off-chain, and then you have some kind of settlement mechanism, let's call this, on the L1 chain where you can post the block, and there's a proof mechanism that like lets you settle whether this block is like canonical or not. There's just kind of broad strokes for context. There's 2 types of these kinds of things. Optimistic rollups, which use like a fraud-proof challenge mechanism, various degrees of real. And then there's ZK rollups that provide like a the fraud proofs are hard for those who are. ZK rollups, on the other hand, that are very expensive to generate, but once you have a proof, you can verify it very succinctly. I'm not gonna like mansplain what a snark is to you guys. I assume most people here know what the concept of like succinct verification is. But at a high level, you can verify the proof without re-executing too much logic. You kind of have like a constant amount of like checking that a point belongs to a polynomial, and that's very simple. And if you can encode the proof into a polynomial, you can do this very succinctly on the L1. And then you can move a lot of this work off-chain. And another clarification, when we talk about zero knowledge, people like to confuse 2 concepts here. There's like zero knowledge that is used for privacy and zero knowledge that is used for scaling. The zero knowledge component is the same, but it's used in like a different kind of architecture and application, where specifically the privacy stuff, you're proving that the execution, you're verifying the execution without having access to the user data, and that's enabled by the proof construction method. The scaling thing, you still need to post all the data, so there's no like, using most of these ZK rollups, there's no privacy component. It's mostly a like compression technology of the compute so that you can just process the succinct verification logic instead of having to re-execute the whole block kind of thing. But emphatically, you still have to post the big data of the block on chain. So there's still kind of a sizable cost there. Yeah, just kind of the state of the world right now. There's like a bunch of these in various degrees of production. See all the orange stage 0s on there. We're early, but yeah, there's like a bunch of these are deployed, various degrees of centralization, decentralization. A lot of them are kind of talking about both decentralizing both the sequencing infrastructure and the proving infrastructure over the next couple of years. And kind of the context for this work was specifically for decentralizing the provers, there needs to be like incentive design around like kind of how do you incentivize people to produce proofs. And a lot of the work that's been done on kind of analyzing the costs of generating these proofs has been very like micro level of like just kind of you take a hash function and you run it a certain amount of times and you see like this system and that system on the same hardware, they like took this amount of time, whereas like there's a lot more that goes into a ZK rollup than just the proof generation. And so we sought to kind of provide like a end-to-end methodology of like how to reason about the cost here. And yeah, I guess that's, yeah, so the first one was like kind of doing an analysis of like just, it's a very heterogeneous kind of environment of like different compilation pipelines, different hardware, different target hardwares, different just like distributed systems, like architectures of like just so a good amount of the work was like doing a qualitative analysis of like kind of what are the commonalities here and how can we reason about the costs. We developed like a methodology that kind of isolates some costs to be like fixed per batch of transactions or blocks that are posted versus kind of costs that are like marginal with respect to transactions, where the kind of the main point here was to try and see like so the different systems end up kind of batching different amounts of transactions into different sized blocks. And by doing this, they kind of managed to amortize the costs differently across time. And so we were trying to like reason about how, like people talk about like scaling in a very like abstract sense, but you want to have like kind of a good idea of like, like given 100, like 10, 100, 1,000, or 10,000 transactions and like chain state that is like this size and so on, like how will this actually scale? And so we were kind of working on analyzing that. And then like another component here that's very important is like, there's the cost of running the proof generation infrastructure, and then there's the cost of what's called like data availability. And I will try to not get too much into defining what data availability is. The Celestia people are here, you should ask them. But generally, like to verify the proof, you need the inputs. The inputs need to be available. The inputs are the data. We want the data to be available. That's data availability. You do this by posting the data to ETH1, and there's like an associated cost of like, you got to put like posting the data on ETH1 means like all the validators have to propagate all this data, and there's like a gas cost to this. And so kind of a main question we were trying to ask is like, okay, like how significant of a component is the cost of like, running all this various degrees of complexity of prover infrastructure of like you have beefy CPUs or clusters of GPUs or whatever you're doing on the cloud. Does that matter? Is this just dominated by DA costs or data availability costs? Because it just kind of, that was like our hypothesis kind of going in. And like spoiler, kind of seems like the situation. Heads up, I will not share results here because we're like trying to hit the AFT deadline and we had to revise a bunch of stuff a couple weeks ago. So the provers are currently running. So unfortunate, but yeah. And then a third goal was kind of to produce like a suite of synthetic workloads and reproducible benchmarks and kind of providing like a dashboard that people can like poke around and see like, okay, like this system, how does it scale given like this stuff? How do the different variables affect that? And just because we couldn't find any kind of like end-to-end thing that would like take the entire infrastructure of a rollup, deploy that, run a given workload on, and like just provide the data for like the community to analyze. And so that's kind of one thing we've been trying to hammer down with this. And then, yeah, just kind of relating this to like existing historical data because like as we mentioned, some of these are in production, and so there is like on-chain data to look at. Yeah, and so this is kind of like a high-level view of like the things that are involved, and this is like specifically not like anyone's architecture. We tried to like kind of go abstract from like staying away from like specific software components and kind of what is the pipeline of things that happen here. And so kind of like the first, like users submit transactions, and then the first like the kind of the RPC that they hit is what people like to call a sequencer. For the sake of this work, the sequencer is just like a dumb like FIFO box that's going to take all the transactions and just feed them in the order that they got them. We like specifically did not get it, like, I work on sequencing for a living. This is not anything to do with sequencing. We just kind of chose the default one. But the sequencer produces batches that are like the kind of like an unexecuted block, you can think about it. And then these blocks are executed to produce like a valid state header and state root and header and so on. This state that has been executed but not proved yet is then like generally posted to eth_1 as like the inputs to the proof. The exact like order of operations differs wildly between these systems. Like they don't all like, some of them post that alongside the proof, some of them have their own sequence of posting this. There's various, but generally like you gotta post the data that goes into the proof. Then you go and you generate the proof, and then you post the proof as well into we can call like settlement or finality, which is contracts on Ethereum L1 where you post the proof and then it verifies the proof against the inputs, and it's like, this is a valid block. And that's kind of the, at a high level, like the main, I guess like the main three costs here to preempt the next couple slides is like, one, posting the data to L1 to make it available. And again, there's like a discussion of like, how is this under the 1559 fee regime? Does this how does this change under proto-dank sharding? There's future things and existing things such as like Celestia and actual data dank sharding that kind of change the cost model even further. And then relating that to the proof generation, and then kind of what are the costs of actually settling, which also kind of differ across the systems. And there's, we'll get into that. But before, so like the main thing the main problem we had starting out is like, you want to have like an apples to apples comparison between the different rollups or between the different systems. And ZK VM design is a field that has like exploded the past 2 years, and there's like 100 different approaches to this, like roughly out there. And so a main part was kind of going over all these like candidate systems and deciding like which ones can we actually like run the same thing on. And just kind of at a high level, like we observed that there's like 2 types of approaches to the implementation. One where they kind of, you think of this as like a general purpose ZK VM, where the VM executes a like RISC-0 is like one example where they execute like a RISC-V like assembly language, and so anything you can compile to that, you can then run on their stuff. Starknet is another one where like they have Cairo, which is like an assembly language that they created where you can kind of compile like quote unquote anything into that, turn complete and so on. This is like in comparison to things like Scroll and Polygon and ZK Sync, which specifically implement like a ZK EVM, where like the ZK VM implementation just, it like corresponds to like EVM opcodes, whereas like with the general purpose ones, you have like an EVM program that you compile into your ZK VM like target thing, and then you run inputs against that, as opposed to like directly correlated, directly like targeting the circuits, and just kind of, this proved to be like denser than we thought, so worth mentioning. But yeah, so the cost model that we kind of worked towards, like figuring out like what data can we analyze around this. The main like separation we did is like batch fixed cost versus like transaction like marginal costs, and so specifically like for each batch, or I think this slide, yeah, okay, nice. So there's things that are like kind of fixed in terms of per batch that you post on, per batch that you post onto, or like settle or whatever you process. There's things that are kind of constant there, where like the obvious one is like the settlement execution. So like you got to run the verifier circuit, and that's that's just like a fixed constant cost for all of them. There's like an additional part that's like proof compression and aggregation, which has like two components to it. One is like the cheapest verifier circuit to use on Ethereum is Groth16. It's very optimized. It's been around for a long time, since 2016, surprisingly, from the name. But all of the, like a trick that almost all of these systems do is like, you run your ZKVM pipeline and stuff, you produce your proof in whatever proof system you choose. If it's a Stark, if it's a Snark, it doesn't matter. You then have a verifier for that target proof system, where the verifier is you have a Groth16 proof system, like a verifier for a Stark that can be verified. There's like a Groth16 based one, and so then you produce a Groth16 proof that you verified the ZKVM proof, and we call that like proof compression. And so almost all of them do this. Another part of this is, and this kind of proves to be very tricky because it differs a lot across the different systems, is you'll have like a proof per batch that was executed, but then some of them end up aggregating multiple batches into a single proof, and then they verify it. So you'll like post like 30 blocks, and then you'll have like a proof that proves the 30 blocks are valid, and then you'll verify that proof rather than each block. And this differs a lot across the different rollups. A lot of them do this, but at different points in the process. And so this kind of gets us to marginal cost, where like, I guess I'll stick with the proof generation first. Like, again, there's some proof aggregation that goes into the actual proof generation. So especially with like folding schemes over the past like year or two, something that a lot of them do is like you'll split the actual work into a bunch of kind of like intermediate state kind of executions, and then you'll have another process that aggregates this back up into like the proof of a whole block, or in some cases the proof of like multiple blocks together. And then obviously, you know, like you got to execute the like actual transaction. That's a component of the proof generation cost as well. And then there's a component here where like each one of these targets a very different both hardware and like kind of distributed systems architecture. So like some of them will target CPU provers, some of them target GPU provers, some of them have like target like a cluster of like hundreds of GPUs in the cloud, and then they do aggregation amongst them. That was like kind of a difficulty in producing like and having the reproducible benchmarks. It's like proved to be like kind of non-trivial to set a lot of this stuff up. And then quick note about like data availability. The like naive way to think about it is just like how many bytes need to be posted. And there's two approaches to this. One is like just posting like the raw transaction data, and then like the transactions just kind of like straightforwardly correspond to how much data you got to post. An optimization on that a lot of people do is you post like state diffs on chain instead of the raw transactions, and then you use that as the input for your proof verification. And then so that kind of like just the amount of data that you have to post like scales differently if you're posting state diffs versus transaction data. There's like a benefit of posting transaction data that like anyone can kind of like reconstruct it from on-chain data. And then like the fee model for like actually doing this changes significantly from the 1559 regime to 4844 regime to, for example, using like something like Celestia, or in the future like Danksharding that kind of employs like a data availability sampling mechanism instead of just kind of posting the data to the chain. Do I have more? I can go into methodology, but I think I'm out of time. No? Okay, yeah. Okay, yeah, so so now we're done with background. Again, something I said earlier, like problem with the existing benchmarks is a lot of them will just kind of take, a lot of the previous work just kind of takes a prover, and you run a hash function on it like 1, 10, 100, 1,000 times, and you see how much time does it take, and you run them all on the same hardware. We specifically like do this like end-to-end thing, so that's slightly different. For doing the fixed costs, we mostly relied on historical analysis of data that was posted on chain over the past kind of year, and then over the past like month or 2 weeks. I forget what we used actually, but for like looking at like what did they pay actually under 1559 versus what are people paying under 4844. Weird stuff with the 4844 stuff because the fees were very low in the beginning, and now they've kind of mellowed out more, or stabilized more. But yeah, that was a bit of work. For the marginal cost, we kind of, there's an element with the marginal cost that's like you don't think about, but the state implementation for Ethereum relies on like the Merkle-Patricia tree, which means that like the bigger your chain is, the more it's gonna cost to like query like data from the state, because you have like a log n cost for, so we tried to like account for that and like the workload that we put through here. And then, what else have I? Yeah, the last point is like, because the architecture, the hardware that all this stuff runs on is vastly different, we compared like each system to itself, we compared like the proof time, but comparing across two systems for the same workload, we compare like the cloud cost of like, you know, like took like an hour here, it took 3 hours there, but like the GPUs were much more expensive than the CPU, so like 3 hours on a CPU may be cheaper than like 1 hour on like 100 GPUs, like that kind of thing. So try to account for that in the logic, in the analysis. But yeah, any questions?
Thank you. I think we're going to take questions offline for this one.